The kinetic theory of gases. Gases behave in certain ways that are described by so-called gas laws. These laws simply describe the behavior. They do not offer any explanations. To provide an explanation, a theory is needed. The theory used to explain how gases behave is called the kinetic theory of gases. Thanks for watching this video, and don't forget to like, subscribe to the channel and activate the notifications. It is very important to the continuity of this channel. The kinetic theory of gases explains the macroscopic properties of gases, such as volume, pressure, and temperature. Therefore, it helps us understand the behavior of gases. We will use the kinetic theory to deduce an equation which relates the macroscopic properties of a gas, pressure, volume, to the microscopic properties of its molecules, mass, and speed. There are four assumptions that form the basis for the theory. Particles, atoms, and molecules are constantly moving in straight lines until they either collide with other particles or with the walls of their container. There is no loss of energy when a particle collides with another particle or the wall of the container. The volume of the particles themselves is so small compared to the volume of the space they occupy that it can be ignored. There are no forces of attraction between particles because they are so far away from each other. Using these assumptions and a little algebra, it's possible to derive the kinetic theory equation. We start by considering a cube with a side length L full of gas molecules. A typical molecule will have a velocity v at any instant, and it will have components of Vx, Vy, and Vz, respectively, in the direction of the three perpendicular axes. We now picture a single molecule of mass m and moving towards the rightmost wall of the container, with a velocity Vx. Each impact of the molecule with that phase reverses the x component of velocity. So the impact changes the x component of its momentum from plus mass times Vx minus mass times Vx. Therefore, the change of its momentum due to the impact is final momentum minus initial momentum. The molecule collides with this phase, moves a distance L to collide with opposite phase, before returning to the same phase. Before this molecule can collide with this phase again, it must travel a distance of 2 times L. Since speed is equal to distance divided by time, time is equal to distance divided by speed. Therefore, the time taken between successive impacts on this phase is given by the equation. In other words, the molecule takes this time in seconds in covering the distance 2 times L. Thus, the molecule collides with this phase after every 2 times L divided by Vx second. This time is the period, and we know the period is the reciprocal of the frequency and vice versa. So the frequency, that is, the number of collisions per second, with this phase is Vx divided by 2 times L. We know the force is the change in momentum divided by time, but we can rewrite this equation in terms of frequency. The average force that the right-hand face of the box exerts on our molecule will be change in momentum times collision frequency. The pressure P of the molecule on the surface is given by the equation. Let's simplify this fraction. Up to now, we have considered the velocity of a molecule in one direction. Now, let us consider the resultant velocity of a molecule in 3 dimensions. We sum Vx and Vy. Remember, that is sum of vectors. We use the Pythagoras theorem. We use Pythagoras theorem again to get the vector velocity. As the motion of the particles is random, we can assume the mean square speed in each direction is the same. Substituting this result into the equation for pressure previously obtained, we get a new equation. This is for one molecule, but there is a large number n of molecules in the box, so we need to multiply by n to find the total pressure. This equation explains pressure. The force of many collisions by many molecules against the walls of a container is what we call pressure. Rearranging the equation, we have the macroscopic properties of the gas, pressure and volume on one side of the equation, and the microscopic properties of the molecules, mass and speed, on the other side. The quantity n times m is the mass of all the molecules of the gas, and this is simply equal to the total mass of the gas. It's worth thinking a little about whether the equation seems to make sense. It should be clear to you that the pressure is proportional to the number of molecules, n. More molecules mean greater pressure. Also, the greater the mass of each molecule, the greater the force it will exert during a collision. The equation also suggests that pressure P is proportional to the average value of the speed squared. This is because if a molecule is moving faster, not only does it strike the container harder, but it also strikes the container more often. The equation suggests that the pressure P is inversely proportional to the volume occupied by the gas. We can see that if a mass of gas occupies a larger volume, the molecules will spend more time in the container of the gas, and less time colliding with the walls, so the pressure will be lower. Now we can compare this equation with the ideal gas equation. The left-hand sides are the same, so the two right-hand sides must also be equal. After simplifying, if we divide both sides by 2, we obtain the familiar expression for kinetic energy. We can see from this equation that the mean kinetic energy of an atom or molecule of an ideal gas gives a measure of the absolute temperature of the gas molecule. If we multiply this equation by the number of molecules, we get the total kinetic energy of n molecules of an ideal gas. If we want to work with the number of moles instead of the number of molecules, we can combine these formulas to get a new expression in terms of the number of moles. Pay attention. At last, but not least, in an ideal gas, there are no long-range intermolecular forces, and as potential energy is associated with intermolecular forces, an ideal gas has no potential energy. Therefore, the internal energy of an ideal gas is entirely kinetic. This means that the total internal energy of an ideal gas is equal to the sum of the kinetic energies of all of its particles. Estimate the average thermal energy of a helium atom at room temperature, the temperature of 10 million Kelvin, the typical core temperature in the case of a star. Do not forget to convert the given temperature to Kelvin. The average thermal energy is the same as the average kinetic energy. Nitrogen gas is sealed in a container at a temperature of 320 kelvins. Calculate the average speed of the molecules. At first, we have to find the mass of a single molecule of nitrogen. The molecular mass is given. So, to get the mass of a single molecule, divide 28 by Avogadro's number. We now take the equation that relates the kinetic energy with temperature to calculate the average speed.